It's a pleasure to be here. So I'm going to be the bad cop. I'm going to keep everybody on track. We have a tight schedule. We do have 5 very interesting talks this morning. And without further ado, I'm going to introduce the speaker, but I'm not going to read their profile, which you have in the program. So the first one is Dr. Francesco Fusco, who's a propulsion engineer here in Boeing in Houston. And he's going to be talking, as you can see here, space launch system, core stage and exploration upper stage. The speakers have 30 minutes. I'm going to stand up when around 28 minutes, and then there will be 5 minutes for questions and answers. Okay? So anyway, Francesco?
All right, thank you. And what I'm going to talk to you today about it is the Space Launch System, shall we say SLS. Particularly, I'm going to focus on the core stage and the upper stage, which is the part that the Boeing, of course, works on it. I'm going to start this by showing you a very short video. It's less than a minute, and I give you fair warning. It's more like a jingle ad for my company, but it's pretty good because it shows you in just under a minute the various phases that are necessary to design and launch a rocket this big, design, testing, and launch a rocket this big. And so it's pretty much will be the agenda of the presentation. I'm going to go dive into the slides to go to those different short section of the video you will see. So let's watch the video. So of course, fair warning say, it's all about Boeing in this video, but that last image you saw, that rocket going up, I was part of the engineer support team for the launch. It was great because I didn't have a real-time duty. That means I was in charge of the 24-hour reports, which means I get there before the launch, and then I have to stay after the launch to do the report, but during the launch, I can go outside and watch. And I was like few feet standing by those guys that you saw putting their hands in the air. And it was amazing. It was a night launch, so it's pitch dark at KSC, and all of a sudden it's daylight. And you don't hear much, but then you start to see the rocket, and all of a sudden the rumble comes and makes your heartbeat going. It was quite an amazing experience. Not so many launches, including in Kazakhstan and things, but that one was particularly effective. Yeah, I've worked on it, so it makes a difference, but let's go into it. I want to share a little things that I don't know if many of you know, but SLS is very particular in terms of contract. And just to talk a little bit about the origin of this project. Typically, NASA has a vision, has a plan. They start to think what they need, and they put out for bid. So different company can go ahead and say, I can build you this for you. And then they award the contract to a company or more company, like for return to LEO, to low Earth orbit. Both Boeing and SpaceX got the contract awarded from NASA. But SLS was awarded to Boeing as a single source, meaning there was no competition for it. And the reason is because Boeing, after CEV, which is Crew Exploration Vehicle, was canceled, they went on and looked at the market and said there was a need, there was a gap. We need an heavy launcher. And so they started to work, leveraging the expertise we had from CEV and from the space shuttle, with the idea of let's try to, use as much as we can already. So try to maximize the reuse of the shuttle technology and the CEV design that we did. Now you would think, wait a second, shuttle is like 45 years old design. You want to settle on something that old? Well, unfortunately, in those 45 years, there was not really a breakthrough in propulsion. I'm a propulsion guy. There's a lot of studies out there. There's a lot of good promises, but nothing really for doing a heavy launcher that will change completely the idea. It's coming, but Boeing knew that there was no, time is always a concern here, right? We have to do things quickly, and so they went off and tried to reuse as much as possible. And that is as part of, I'm gonna try to highlight what is coming from the shuttle. So when then NASA decided, yeah, we need an heavy launcher, of course, Boeing was like a year advanced, and that's without the time of the contract in place. So they decided to go single source. And that's why we ended up building this thing. So the core stage that you see here is divided in 5 sections. The first one is the engine section, and he's using the same main engine of the space shuttle. It's the RS-25. It's a very reliable engine. It's used liquid hydrogen, liquid oxygen, built by Aerojet Rocketdyne. They're the same engine, although they're changing it a little bit. Shuttle was reusable. This one is not. This get disposed after bring the Orion to orbit. So the engine doesn't need to be that strong like they used to be for the shuttle. So Aerojet Rocketdyne is redesigning them to maximize their performance. They are actually also improved the throttle settings that we can go to, and they're testing it right now, like in those days. In this section also is the thrust vector control. That is the system that my team was assigned to it. So I worked on the design, analysis, and testing of the thrust vector control, which is the hydraulics that moves those engines. And again, a lot came from the space shuttle. We even used some pump, like circulation pump is the same pump that was used for the space shuttle, actually the same hardware that was sitting there. We had spares, and we're using it for the flights, for the first 3 Artemis. So I'm going to talk a little bit about the Artemis mission overall as well. The second section here is the liquid hydrogen tank. As you see, it's 537,000 gallons. It's a huge tank, and you have to keep the hydrogen very cold, minus 423 F. Hydrogen, very low density, so in order to pack the mass you need for your rocket, you really have to keep it cold. That is it is not just keeping this cold, is to load. You have to load it quickly because you build up pressures, you can get the moisture in the air, and we launch from Florida, which is as humid as your worst. So you have ice forming outside, and the tank try to insulate you as best as they can, but of course it's limited, it has to be light, so there's a lot going on to try to protect that. But these are the same type of issues we had with the space shuttle, of course. But you have to be able to load a few hours before the launch. And so Stanley Space Center, and I was part of that team too, was when we did the green run, that's where we finalized how to load that quickly, this very cold propellant. It's very challenging. I mean, a lot of systems, they don't like to be that cold. So you need to figure out a way to load while you're protecting the other hardware, and it was not straightforward. It took several tries. We did a lot of wet dress rehearsal, we called. This whole campaign, which I supported, was during COVID. It was crazy. There was really nothing else to do. We were working like 14, 15 hours a day. We couldn't even go to a restaurant in Mississippi. So it was a kind of experience. But then keep going on the different section. You have the intertank that connects the two tanks, of course, and it's also the main touching point for the solid rocket booster. We're going to talk a little bit about next slide. And then the oxygen tank. As you see, the oxygen tank only 196,000 gallons and only minus 297 degrees F. Oxygen, of course, it's more dense than hydrogen, but don't let you fool. The mass of the oxygen is actually higher than the hydrogen. Those engines works with the 6:1 mixture ratio. Mixture ratio is basically the ratio between the mass flow of mass flow of the oxidizer over the fuel. And then finally, there's the forward skirt. It's basically the brain of the rockets. It has like all the flight computers, the avionics. But as you see here, there's 4 major sites. They are the center of excellence for those 4 major operations: is design, build, testing, and launch. Houston is not there, but there's a good group of engineers, me one of them, here in Houston, that works on the design, analysis, and testing as well. And they also support real-time operation. So we'll talk a little bit about the MAF now, which is the, there you go, is the manufacturing facility. This center was kind of ran down before SLS start. There was not much going on there. Right now it became one of the central excellence. It's amazing what they were able to do in those 7, 8 years. We built the tanks there, and for Artemis 1 and Artemis 2, we also installed the engines. The engines, of course, are shipped by Aerojet Rocketdyne. So we did the integration of the core stage at MAF, and then send it to the VAB and KSC, where we stuck the rest of the vehicle. We did that for Artemis 1 and Artemis 2, but from the following, actually the engine would be shipped directly to VAB, and the assemble will be done vertically. At MAF, we do it horizontal. So the operation is still changing a little bit, but MAF definitely, it's amazing. It's just outside of New Orleans, amazing site to visit. The VAB is, it was built in 1966, I think, to under the Saturn V project. We're supposed to host up to 4 Saturn V at the same time. Those high bays are amazing. I mean, if you look at here, you have all those different levels that you can literally access every port on the vehicle. I used to be in there also for the shuttle, and it was amazing as well. But the feeling I got by being in front of this rocket was particular. You are in the building and you have this massive rocket standing there inside with you. It's quite a treat. We hosted like 2 shuttles at the same time. We could host them on a high bay. But this gives you access to everything. And so in the VAB, you do the entire stack. So the different parts come in. As I said, now also the engine, actually you don't see it anywhere in these pictures, will be assembled. But then they have to keep building on top of the core stage. And we see next slide what they're going to build. And if you look closely, there's also some shady guy there with a safety hat that I'm pretty sure is Italian. So if we look at the overall assembly of the SLS, so we talk about the core stage with this RS-25 engines. What I didn't mention is the capability of those engines. Each engine produces about 500,000 pounds of force, 500,000 pounds of force. It's quite impressive. And the 4 combined is more than 2 million pounds. But now we're going to talk about this little guy. Those are the solid rocket booster. Again, it comes from a shuttle-derived idea. I know Van Brown that was sitting there in Alabama where this was designed, told us never to fly human on a solid propellant. The reason why you don't want to really fly on a solid propellant is because you can't really test it. Like we have a requirement for NASA to test all the liquid engine, and you can test them. Take it in a test cell if they're space, or you can test on the ground if they're lift-off engines. Then you refurbish some parts, you clean them up, and you reinstall those engines. But for the solid rocket booster, you can't really do it. I mean, you can test one of the production, but you can test the one you're going to use because all the engine is basically this solid propellant. A solid rocket booster use aluminum powder as a fuel, and they use ammonium perchloride as an oxidizer. Of course, they have a copolymer bonding those two together to create the grain of the propellant that burns. But it's quite amazing that the way that they work. We never really had a problem with the combustion itself. The problem on the Challenger that some of you might know that was caused indirectly by solid rocket booster was not due to the propellant itself. It was due from a defective O-ring and the cold exposed. But I'm not going to be challenged, or we're going to run out of time fairly quick here. But those are capable of burning about 6 tons of propellant per second. And they produce 3.6 million pounds of thrust each. So we are talking about these two rockets are the 75% of the thrust at takeoff. Of course, they burn that propellant very quickly, so they're done in 2 minutes. So after 2 minutes, they detach, they fall into the ocean. Now for the space shuttle, we used to recover them. For SLS, we don't. So they're improving those. They're lighter because, again, they don't need to be reused. But they're doing a lot of work because SLS comes in 3 different variations, 95, 105, and 130 metric tons. The 130 metric tons will be basically for the core stage will be everything will be the same. The things that really change is the improved solid rocket booster, which ATK and Northrop Grumman are working on it. They're divided in 3 sections as well. You have the aft assembly, the motor assembly, and the forward assembly. The aft assembly has the nozzle and also has a thrust vector control that you can direction the thrust. The motor assembly is divided in 5 sections, and the forward, of course, there's there's the attachment point to the core stage, of course, but there's also all the avionics and the computer you need to run the rocket. If we go up, so we started from the bottom going up, this is the vehicle stage adapter. This is to allow the use of the ICPS and host the ICPS. ICPS is the upper stage that we use for Artemis 1, 2, and 3. It will be changed then going forward with the EUS, the exploration upper stage, which is a lot more capable. But basically, this is the orbit stage. So once you get to orbit, you lose this after 2 minutes. You lose the core stage. The main engine will continue to go up to 8 minutes into the launch, so 6 minutes after you dispose of the boosters. And then after 8 minutes, this will be disposed, and you're left with the ICPS, which is the one that will do your TLI, your translunar injection. And this is where all the capabilities needs to rely. And we'll see why EUS is so important. And then, of course, you have the adapter for the Orion capsule, some panels, and these on top, those 3 components are the Orion capsule. You have a service module. Service module was built by the European Space Agency, but again, is using a lot of shuttle stuff. The main engine is the orbital maneuvering system of the shuttle. The shuttle had 2. This one has only 1. But we use like the same engines. Like Artemis 1 used an engine that came off the shuttle, flew 19 missions with the shuttle, and then we flew for Artemis 1. Then you have the crew capsule itself. Of course, the service module uses different kind of propellant. That's actually my expertise, is hypergolic propellant. It's using monomethyl hydrogen and nitrogen tetroxide. Those work really well in space because they don't need an ignition source. When they get in contact in the combustion chamber, they just burn spontaneously. That makes it a lot easier to do it in space where ignition is fairly complicated. The Orion crew also has some thruster on it, but those are like smaller thruster. They're usually monoprop, hydrogen on a catalytic bed. And then finally, you have the launch abort system. That's the tower that's supposed to take the crew to safety in case of an abort. And those are solid propellant as well. Try to look at the time here. So for right now, we're focusing on 2 evolutions. So the one that we just flew was the SLS Block 1 that had the ICPS, as I said, and it's very limited as 1 RL-10 engines, again made by Aerojet Rocketdyne. They have about 25,000 pounds of thrust using liquid hydrogen and liquid oxygen as well. But eventually, after Artemis 3, we will move to the Block 1B that will host the EUS. EUS will bring some unprecedented capability. He has 4 RL-10 engines, so it's pretty much quadruple the amount of cargo that you can deliver. You can get up to 43 metric ton to TLI, which is unprecedented. Nobody can send this kind of cargo to the moon, which the project that I've NASA, and we're going to look a little bit into that, we definitely will need this sort of upper stage to achieve. There's also an SLS Block 2 that is not showed here because it's still in work in progress. But again, the big difference there will be some improved solid rocket booster. And so this is the rendering of the EUS. And again, underline here the fact that it can deliver up to 42 metric tons to translunar injection. And it's definitely also the fairing, the size of what it can carry. And that's going to be fundamental to build a gateway, so a space station around the moon, basically. So that's why SLS is really the stepping stone of the whole Artemis project. Because if we take a look at the approach that NASA had in those few years, the idea was like, we were in a phase 0 where, we had the space station flying, and we were doing science on the space station, trying to figure out all the challenge to go to space. In the meantime, we were building capability like the SLS and others. We're still working on several parts of this project, of course. And then in the 2020s, we started to do cislunar operation, so go back to the moon. And so that's what we did last year. Artemis 1, which I'm going to talk a little about in the next slide, landed like a few days ago, a year ago, a few days ago, we celebrated 1 year of the landing. And eventually, you're going to, in the 2020s, you're going to put, again, astronauts on the lunar soil. Then we're going to start to do deep space exploration. And so the idea is to do a gateway around the moon so you can facilitate access to the moon itself. Then eventually start to move with a deep space transportation system to move to Mars and beyond. So Artemis 1, or Artemis 1, how they say here. Pretty much the sequence, it's going to be similar for all of them. So, but basically you have, you start from KSC, Kennedy Space Center in Florida. And the first part is like you have all the engine, the 2 solid rocket booster and the 4 RS-25 producing 8.8 million pound of thrust. They'll take you up off the ground. After 2 minutes, the solid rocket booster detached. As I say, they fall into the ocean. They're not being retrieved. After 6 more minutes, the core stage actually exhausts their fuel, so they detach as well. And now you're left with the ICPS. So you do a raise maneuver to high orbit. Then you check your system before you commit to the lunar orbit. When you're ready to go, the ICPS did the TLI burn. After doing the burn, you kind of detach. You deploy your solar array. And now at this point, the entire propulsion system is passed back to the Orion capsule. So you have the service module with several engines, smaller engine and the big ohms. But basically that push that the ICPS gave him, it was good to coast you all the way to the moon. Then the ICPS did a very interesting disposal maneuver by itself, doing a flyby by the moon. And that's what to test additional system on the control of the ICPS. When you get in the proximity of the moon, they initiated a flyby, and we ended up firing a thruster to enter DRO orbit. It's a distant retrograde orbit, and that was one of the achievements for Artemis 1. We flew about 40,000 miles, more than 40,000 miles, on the back side of the moon. That's basically the furthest that a human-rated vehicle ever flew in space. It was robotic. We have different, but the Saturn never went that far. And so it was quite an achievement. And of course, then we did a return with a power flyby. And basically, you go coast all the way to re-enter on Earth. where the service module help you setting up the right pad on with the orbit bird, and then it detached and it get disposed as well, and the crew module actually re-entry and does a splashdown using the parachute and landing in the ocean, and is retrieved by a US Navy ship. This mission was a huge success. I mean, it was almost flawless. I mean, everything was, a lot of analysis and testing went before this, but at the end, it all paid off. I mean, we were staggered. Like for core stage that I was supporting, my 24-hour report was nothing to report. I mean, I had to show the data, but it was like everything worked. So it's quite amazing for the first launch of a vehicle. So what's next? So it's scheduled not earlier than November 2024. You know, that's how we gave schedule here in the space business, not earlier than, because things can happen all the time. But hopefully next year, we'll fly Artemis 2. It's going to be quite different. This is going to have crew on it. So you're testing also now the ECLAS system and, you know, all the system that for crew sustainment. And they're also going to do prox operation. As you see, the trajectory is quite different. And there's a big reason for it. We don't do much around the moon. This is probably a 10 days mission. What we're going to do here, the first part is pretty much the same, right? You get to the orbit. Then you use the ICPS to go to a high orbit. And at that point, you detach the ICPS. So the ICPS will not do the TLI burn for Artemis 2, because we're going to use the ICPS to conduct prox operation. So manual prox operation, the astronauts will exercise and will use the ICPS as a target. And once they complete that operation, ICPS will be detached, and at that point your TLI will be done by the Orion main propulsion system, which is the orbital maneuvering system engine. And of course, it's going to use, you know, it's a single burn that puts you on a free return path. So you basically are on the orbit and naturally will go around the moon and return towards Earth. And then, of course, the service module will also help to the orbit burn and make sure that the crew module re-entry safely. The service module, a funny story, they tested next to the Starliner service module. So I was the test conductor for the Starliner service module. And of course, on the other side, the service module of the Orion ended up like next to each other. So we were sharing the same control room, the same blockhouse, you know, to test those engines. You are not far, but you are in a blockhouse that has 6 feet walls and closed completely, no windows with the external, because, you know, if something happens, you need to be protected. And I was told, you're not supposed to talk with the European. You know, the European Space Agency was coming in with Airbus. We were Boeing, so it was big things going on. And then I'm getting to the control room, and actually the one that was directing there was an Italian. It was a friend of mine. That was the end of all the not talking with the European kind of things. Of course, I tell them, but I am European. What do you mean? I don't have to talk with myself? So it's kind of weird. But yeah, that was a big campaign for both of us. We had a lot of problem for the service module development. You know, that's the first time you do the integrated system test. And although you can do all the analysis you want, there's always things that are going to happen and you have to fix after doing tests. And both of us, a lot of lessons learned from those testing. But the service module, besides giving the propulsion, it also provide water and air and thus some thermal control system of the crew module. So that's why they want to keep the service module until the very end. And then there's some autonomy with the crew, with the capsule itself. But the service module is quite unique for Orion in that regard, because usually service module are just for the engine. And finally, we talk about Artemis 3. This is still down the road. Not all the parts of this mission has been all figured out yet. But basically the idea is to announce land astronaut on the moon. So after the first phase, it's always the same. So core stage stays pretty much similar. You're now going to use the ICPS to do your TLI, because what you need to conserve as much propellant as you can in the Orion capsule to do then lunar operation once you get there. And the way that NASA envisioned this, we're going to set up, and that's what Orion will do. will set up on what we refer our NRHO orbit. That stands for Near Rectilinear Halo Orbit. It's a very particular orbit, and Orion is going to put there, and so the 4 astronauts will be on the ship, and 2 will use the lunar lander to go on the moon. Now, we don't have the lunar lander yet. I mean, I think SpaceX won the contract and is still working on it. And that's one of the big parts that is missing in this one. But eventually we'll have one. And so the 2 astronauts will go on the moon. They will do some exploration. Part will be in the ship, part will be outside, so they will go outside as well. And then basically they will return into this in this lunar orbit to dock again with Orion capsule, and they will return. But that orbit is the same orbit where NASA is thinking to put the Gateway. So the Gateway will be in that orbit, so when we have one, Orion can comes in, dock to the station, and it will make all the lunar operation a lot more easier and a lot more effective. And then, of course, there's the linear. Well, you do again the re-entry in a similar fashion, and you re-enter with your 11 parachute and then splash down. Still a lot of work to do for this, but as we always say, we're going to take it one step at a time. And I think I'm getting warning here that I'm running out of time. And I want to leave some time for questions. So thank you. And if there is any questions, I'm here to answer them if I can. Thank you.
Exemplary speaker, kept on time and left about 6 minutes for questions, so we have plenty of time for some questions. I'm not sure whether they need a microphone or not. Speak loud, okay? So, yeah.
Yeah.
If you speak loud, I think it's right over here.
Yeah, I can. So my question is about the propulsion system. You said that a lot of technology comes from the space shuttle.
For SLS, yes.
And one limitation, I mean, I'm not from that field, so my view is pretty general, is the cost of launching stuff in space, which kind of limits the application, right? For example, in astronomy, the weight that you can put on your rocket and so forth. So what is the key to lower the cost? Is trying to find a better technology for the propulsion system, or just to make your system more efficient with the old technology?
I mean, a little bit of both, but there's some limitation on how efficient you can be with this type of propulsion. We've been trying to optimize as best for those next 40 years, so we're getting very close to. There's very little things you can do. Some material are getting better, lighter, and strong the way that you need it, and withstand those temperatures. But really, you need that breakthrough. And there's a lot of studies, and there's some got to fruition, but nothing that is ready to go. And they all have some sort of challenge. The first thing that comes into mind, I don't know if you're familiar with the plasma thruster that Chang Dietz built. He started at NASA. When I first come here in '99 for my internship, I met him at the lab, where he was at JSC at this big building where he was building this amazing engine. It works. The engine works. I mean, now it's off-site, it's his own company, but they built it. It's there, it's ready, and it works. The problem, though, is the electrical energy that it needs, right? And so they try all kinds of approach to it. I mean, if you want to use solar panel, you will need like 10 football field worth of solar to provide the amount of energy that those antenna needs to make this plasma thruster to work. They think about nuclear, but there's a lot of other complications. So the technology is making progress, and there are ways to optimize space flight. But at the moment, we don't have a clear path yet for any of those technology. Although, again, a lot of progress has been made. And if you see even SpaceX, right, that is come in with a novelty approach, trying to do things differently. If you Starship, they still use a liquid propellant. I mean, they choose a different path. I think they use so-called methane, so it's not a cryo. But you see, they're having problem to lift off. I mean, actually, they lift off okay now, but something happened a mile away, so they're still figuring things out. But again, they're using chemical propellant technology, which is the one we were using before.
One question here.
Yep.
I'm just wondering, it seems like there's a lot of heat that's generated at every stage that's not captured. Would there be a way to kind of capture that heat and co-generate electricity to be able to then charge something to be able to use it later? Have we thought about capturing the heat at each stage to generate electricity? I'm just wondering.
So there are things that you do, like, you know, the way that the RS-25 works is like actually the fuel goes and cool off the chamber, the nozzle, and then returns into the chamber. That's some energy saving kind of thing. It does two effects for you, right? It energizes the fuel, but also it cool off the chamber that is getting to crazy degree. The problem is that heat is your enemy in that case, right? You need to get rid of it because you get so much heat that it might melt stuff. So it's really, and those operations, the burns are very short. For liquid propellant, you have a burn that lasts, well, to take off, as I say, minutes, right? 2 minutes for the solid rocket booster, 8 for the core stage. In space, it's even less, you know, like all the burns you see in minutes. And so it's not really worth it to try to capture that energy that will require a lot more effort to do it for just those few minutes that you use your engine.
One quick question.
I think I could just comment on there are thermionic systems that can convert waste heat into electricity, but not for, as Francesco says, that's not really efficient for launch operations. But there are some ideas for surface operations and how you can convert. And then, because we have a big problem on the moon with surviving the night, and so the ability to store energy, create energy from working systems is there. I just think, I mean, the key thing, and to Andrea's question too, I think you're right. I mean, you need a big rocket to get into these transfers. And where they're saving money is on the cargo supply for the crew when they go to the moon. So they're working with SpaceX and other companies to have resupply, and then they can use their reusable rockets. They don't need quite the capability that Boeing's putting that needs for the SLS. So there's a lot of work going into the whole infrastructure comment, and getting there is just the hardest part, right? And funding the rest is challenging.
Yeah, and it's kind of what they're trying to do on the moon, right? They have that orbiting station, so you can actually go to that station. And now SpaceX is proposing to do in 2 stages to get to the moon. So their rocket is going to have less capability from Earth because it's going to go to an orbit, and then they are supposed to do a second launch where they basically refuel at this location, and then they can go to the moon. It's another type of approach. A lot has been taught. There's challenging there too. So at the end of the day, I'm running a program with students to try to design a mission to Mars, and we always offer we always say here those type of combination, and each of them really requires a lot of ops operation are really difficult. Refueling operation are difficult for big rockets and things like that. But SpaceX is working in that regard. But I thought your question was specific on propulsion, right? On what type of evolution we can do for propulsion. There are some in the work in progress, but still nothing that we can use at the moment.
Thank you, Francesco. With that,
thank you.
I'm sure you'll be around at lunch to ask some additional questions.
Absolutely.